So a system can exchange energy with its surrounding by heat and work, and we've talked about both of them now. Heat, Q, is mc delta T, and pressure volume work is negative P times the change in volume. And we can have both of these going in the same direction, or they can be going in opposite directions. Any combination is possible here. So the reason we're talking about all of this is we want to be able to get at what is the energy change during a chemical reaction. So the internal energy change is going to be all the heat and work that's exchanged with the surroundings. So delta E is Q plus W. If we keep everything at a constant volume, we don't allow the volume to change, then W becomes 0, because W is negative P delta V. And if this is 0, then W is 0. And then we end up with the change in internal energy for the chemical reaction being equal to the heat at constant volume. It isn't practical to measure the temperatures of the individual reactants and products. I mean, I would go so far as to say it's not really even possible. So instead what we do is we measure the temperature of the surroundings, and so we can then calculate how much energy was given off by the chemical reaction, because we see the change in temperature of the surroundings. And if we're doing this at constant volume, we would use something called a bomb calorimeter. So then the surroundings will be the bomb calorimeter, and we'll see that the system, Q for the system, which is the reaction we're interested in, there's negative Q for the surroundings, and here we have made that to be the heat absorbed or released by the calorimeter. Calorimetry is a technique in which we measure the heat of reaction by looking at temperature changes. So this is a bomb calorimeter, very high-tech and fancy. Well, kind of high-tech. There's a sealed container in here that's called the bomb. Nothing explodes. We have our sample in here, there's oxygen in here, and we have a remote ignition. So this is generally used for combustion reactions. You could stick a peanut in there and burn it and find out how much energy is stored in a peanut. Around the bomb, we have water with a thermometer so that we can measure the temperature change in the water, and we've got stirring so that we make sure that everything comes to the right, even temperature. So we're going to use a calorimeter constant. The calorimeter constant essentially, is the mass of the calorimeter times its specific heat capacity. The mass of the calorimeter is not going to change. The specific heat capacity is not going to change. So they generally lump those two together in one constant instead of multiplying by the mass all the time. So Q for the calorimeter is that calorimeter constant times the change in T, temperature, and that is equal but opposite in sign to the heat for the reaction. Delta E is the heat for the reaction. Any questions? So here's an example. When 1.550 grams of liquid hexane undergoes combustion in a bomb calorimeter, the temperature rises from 25.87 degrees Celsius to 38.13 degrees Celsius. Find delta E reaction for the reaction in kilojoules per mole hexane. The heat capacity of the bomb calorimeter determined in a separate experiment is 5.73 kilojoules per degree Celsius. Again, lots of words and lots of numbers. So there we've got a mass, we have a temperature, this is temperature change, we've got a heat capacity, And then they're asking us to find the change in internal energy for the reaction in kilojoules per mole of hexane. So we know that delta E for the reaction is equal to Q for the reaction because this is at constant volume, so the work is 0. And so that's going to be equal to negative Q for the calorimeter. So we're going to look, we can calculate how much energy was absorbed by the calorimeter, and then we know that that was the amount lost by the reaction. So we have Q for the calorimeter is going to be equal to C for the calorimeter times the change in temperature for the calorimeter. So we had an initial temperature of 25.87 degrees Celsius, a final temperature of 38.13 degrees Celsius. So I can take 38.13 and subtract 25.87, and the change in temperature is 22.26 degrees Celsius. They gave me the heat capacity for the calorimeter. This has units of kilojoules per degree Celsius. Specific heat capacities have joules per gram degree Celsius. So I've got my two values there that I need so I can calculate Q for the calorimeter. So 5.73 kilojoules per degree Celsius times 12.26 degrees Celsius. So somebody please check my math. We'll blame it on my calculator. So that is Q for the calorimeter, assuming I didn't screw it up. So then delta E for the reaction is equal to negative Q for the calorimeter. So that's negative 70.249 kilojoules. Is the amount of heat released going to depend on how much butane burned? Yeah. You burn a little bit of butane, you get a little bit of heat. You burn a lot of butane, you burn a lot of heat. So having this, we could say that that's negative 70.249 kilojoules per 1.550 grams of hexane. Okay with that? Because this is what we burned. This is the amount of heat released for that amount that we burned. But they want this in kilojoules per mole of hexane. Of course they do, because it's chemistry and everything's about the mole. So what we want to do is we want to take this mass and calculate the moles. So I've got that many grams, and I can calculate the molar mass of hexane as 6 times 12.01 plus 14 times 1.008. So I want to divide by grams and multiply by moles. This is molar mass thing we learned a while ago. So 1.550 divided by 86.172, 0.0179. 9, 8, 4 sig figs, 7, 3 moles. So I'm going to take my amount of energy there, 70.249, and divide it by the number of moles. And I believe I should have 3 sig figs. So this would be best expressed as, oh, I lost my negative sign. Kind of important. Oh, yeah, that's the only place. Negative 3.91. This is the digit I'm keeping. The next digit's 5. I have to round up. Times 10 to the, and I'm moving the decimal point 1, 2, 3 places. It's a big number, so it's a positive exponent, kilojoules per mole. Any questions? Yay, got one right.